Inside of this beaker is a blue solution. So there are molecules inside, they're blue dye molecules, which make this solution appear blue. And then there's also water that's creating some amount of volume. And if we take this and we measure out some amount, so there's about 30 milliliters of the blue dye, and then we add in some water, we're not changing the number of blue dye molecules, but we are changing the concentration of the solution. That is to say, how many blue dye molecules there are compared to how much water there is. And this is going to give rise to two important phenomena: the idea of dilution and the idea of absorption. And this video is going to focus on the idea of absorption, which is going to be described in terms of Beer's law. So if we look at Beer's law, we've got an equation that's going to relate the absorption of the solution to the concentration of the solution. And how much light is absorbed is going to depend on the concentration. That is to say, if there are more blue molecules inside of here, it's going to have more light absorbed. That is to say, it's going to have less light get through. Now, how much light gets through is also going to depend not just on concentration, but it's also going to depend on path length. That is to say, how far the light has to travel through. So if you've got something that's thicker or even larger, you're going to have some path length associated with that. That is to say, how much the light has to travel through to get from one side to the other. It's going to run into more molecules, and that's going to give rise to more absorption. And then there's also the chemical compound and how the blue dye molecules inside of this interact with the light. In order to get at that chemical relationship, we have this parameter epsilon, called the molar absorptivity. Absorbance has no units. It's a ratio of the intensity of the light before the sample and the intensity of the light after the sample. And because it's a ratio, you end up with no units. B is path length. And in most cases, most experimental cases, it's going to be 1 centimeter. If you look at the absorption video that's in the class notes on the Canvas page, you'll notice that we used a plastic little cuvette. I'm sorry I forgot to bring one. But that's going to be a 1 centimeter path length, and typically in experimental cases, that's a set value chosen by our experimental setup. Epsilon is the molar absorptivity. It is going to have units that make it so this entire equation work out. Its units are typically going to be, now we want it to be no units on one side, so we've got to cancel out the path length and the concentration. So you're going to get 1 over centimeter times 1 over molarity, using molarity as our unit of concentration, the typical unit of concentration we'll be using in this class. In addition, we've also got C, which is going to be our concentration, which will be in units of molarity, which is also moles over liters. Now the concentration is going to be set by how we're preparing our solution. The path length is going to be set by how we are setting up our experiment. And the epsilon, the molar absorptivity, is going to be set by the chemical compounds that we're looking at. And the absorption is going to be something we measure. If we know any 3 of these parameters, we can create a relationship and figure out the other. So we can run into situations where we know the concentration of the path length, and then we can measure the absorbance to understand the molar absorptivity, or we could know the path length, the molar absorptivity, and measure the absorbance to understand the concentration. There's a lot of different ways we can use this equation, but it's almost always going to come down to knowing 2 parameters, measuring the third, and solving for the fourth. And we can think about this, again, in terms of these solutions. If you look at this, I can try to increase the concentration. So let's try diluting the concentration a lot. I'm going to add a whole lot of water. And I don't know if you can tell on camera, because as I'm looking at this just in front of me, the color has gotten a lot lighter. Instead, by comparison to this much higher concentration situation. So these are the same blue dye molecules, approximately the same path length. They've got similar path lengths, but not exactly the same. But they have different concentrations, and we can see that difference in absorbance. Typically, rather than just eyeballing it, saying one's more concentrated than the other, we would use a spectrometer to actually measure the absorbance with some sort of standardized curve. So with this, now we can start to think about molar absorptivity and how we can use this equation. Most importantly, though, I want to focus on molar absorptivity for just a moment longer and talk about what gives rise to molar absorptivity. Path length is pretty straightforward. It's the length, it's the light distance traveled inside the solution, not to be confused with wavelength. Path length is different. Absorbance is just how much light is making it through, or rather, how much light isn't making it through. Concentration is this idea of how many molecules in your solution. Molar absorptivity is going to depend on the identity of chemical, and it will depend on the wavelength of observation. Right? So what this means is a blue solution is going to absorb light in a different way than a red solution or any other chemical compound. And also, this solution is going to absorb light differently in different parts of the visible spectrum. That's where this wavelength of observation comes in. Right now, we're looking at it with all possible wavelengths, and we can see it has this blue color. This means that it's interacting with the visible spectrum in a particular way, and using a spectrometer, we can see that particularity of the wavelengths of observation, how that changes. We can actually use this information to get at chemical information inside the solution. So this is the base idea of Beer's law. Hopefully that helps make sense of the background reading for the absorption lab and some of the calculations you need to do. In another video, I will do 1 or 2 Beer's law calculations for you to look at as well.